a node and you just initialized one node, and say all you did was just malloc for the root, and then in the definition of the struct is 2 pointers to 2 other nodes. By default, are those nodes null, or do you have to zero them out to null?
Zero them out.
Just to be safe?
Yeah. So on the server, it seems like they're null, but there's a special routine you can use to load zeros into malloc memory, which suggests that that's not part of malloc's original charter.
Just use malloc.
Yeah.
So I just hit the node left equals null.
Yeah.
Is that necessary to write that then, or?
I would definitely recommend it.
Okay.
You may get away with it on a Linux server, but if I look closely enough at your code, and I'll look at your code now, and I don't see that, I'll definitely at least comment, and I'll probably take off a few points.
I'm going to be.
Because you really want to be sure that
I'm
those
fixing
things,
mine right now.
that those things are null.
The other thing is, if you're malloc,
Said that would be
you
pre-coded.
Yeah.
somewhere else you can set it null and you create it, then it's really bad if you don't set it null.
All right, so what does a node in a tree look like? There's a pointer to the left, which is pointing to a struct node. Let's say there's integer data, which there is for these ODPs. And then there's a pointer to the right. And I'm going to set up a couple of type defs, so we don't have to keep writing struct node star. So I'm going to type def struct node star. I'm going to call this a tree. And I'm also going to type def a struct node star and call that a node with a big N. So I got a couple of type defs available. So let's insert into a tree. So here's an existing tree. You don't have to copy this down, play along. So here's a binary search tree. And suppose we want to insert, I don't know, give me a number.
56.
What was it? 56. I like that one better than 42 for some reason. So how do we insert into this tree on paper? We start at the root. There's a 40, we're trying to insert 56. We know everything bigger than 40 has to be off to the right. So we move down to the right and we look here and here's a 60. And 56 is smaller than 60, so we move down to the left. And here's a 55, 56 is bigger than 55, so we move down to the right, but there's nowhere to go. So we create our new node and we make that the right child. Okay, can we write code to do that? Absolutely. So let's write an insert routine. It takes a tree and it takes an integer. And pseudocode, here's what I'm going to do. Temp equals t. So I'm starting off, temp is going to point at the root of our tree. And let me take our 56 out of here. So here's what I'm going to do. If temp arrow data is bigger than n, I want to move to the left. So I'm going to say temp equals temp arrow left. And then I'm going to go to the top of my loop. I got a go-to in a 215 programming assignment this morning. I'm so excited. Never see go-tos anymore. Can't recommend you do it in here, but I appreciated it. So compare our data to the root data, and if our data is smaller, just move our temporary pointer down to the left. So now temp points here, and we come back up to the top and we say, is our temporary data 20 bigger than our number n56? No, it's not. So if this is true, we want to move to the left. Otherwise, we want to move to the right. So we say temp equals temp arrow right. And we come back up. So we'll move temp to temp arrow right, which is, why the heck did I go left? So temp's pointing here. Temp data is not bigger than n, so we're going to move temp to temp arrow right. So temp points here. We come back to the top. Is temp data 60 bigger than 56? Yes. So set temp equal to temp arrow left. So now temp points to right here. And is temp data 55 bigger than 56? No. So we're going to say temp equals temp arrow right. And when we set temp equal to temp arrow right, temp's going to become null. And now we're in trouble. So we don't want to do another loop here. We want to move to the right, but the thing on the right is null. That tells us put your new node on the right of temp. So before we move to the left or the right, we need to check something. If temp arrow left equals null, then we want to say temp arrow left equals new. So up here we needed to create new equals whatever we have to do to create a new node. That can be your init routine. Malloc a node, set the data equal to n, set the left and right children to null. So that's all subsumed in this line with squiggles, etc., etc. Pseudocode. And then we return. And down here, if we're going to move to the right, before we do that, we say if temp arrow right equals null, then set the right child to be our new node. And return. So far, so good. This is almost going to work. We gotta be a little cautious with the return value from this insert function. Because what happens when we start off and t is null? We have no nodes, and we say insert some number into this empty tree. We're going to create a new node containing our first piece of data. And right here, we're going to say, see what temp's data value is, and we're going to say false, because temp is null. So in the special case where our tree is null to begin with, all we want to do is create a new node and make that the root. Well, if I set t equal to null, that might feel good, but it's not going to change the root of the tree when we call this. So here's how we're going to run this. So here's our main program, and we can say tree t equals null. And if we say insert t comma 40, that's not going to change the value of t in my main program. Even if I say t equals new, that's not going to change the value of this variable t. Why? Because c is passed by value. when I call insert, I'm not passing this variable, I'm passing the value of it. And my subroutine makes a local variable called t and sets it equal to the same value as my t, which is null. It'll check to see if it's null, it'll change t to point to my new node. When I come back here, t is still null. So my insert routine really needs to return a pointer to a struct node.
Or you just add extra asterisks.
I could add an ampersand in there, and I'm not going to. Then we're going to have a struct node star star, and that's a whole nother.
Those are fun.
They are fun. So I'm just going to return a struct node star, a pointer to a tree. And normally, this is just going to be the same thing as the tree that I pass in. The one exception is if my tree is originally null, this will return something different. It'll be a pointer to the new root. So in the beginning here, I can say if t equals null, just return my new node. And in these cases, I can just return the original root. This is not a bad thing to code up and step through. And the main things to step through are the first case where you start with an empty tree and you actually add a root node to it. And take a look at the value of t before you call insert, and then step through insert and watch what happens, and then come back and see how t changes. And look in memory and you should see a null pointer, the value that you inserted, and a null pointer. And then call insert again. So t equals insert, say t comma 20. And you should see temp pointing to your root node, temp will change to be temp arrow left, and it'll come back up here, and temp arrow left will be null, and then it'll change that to point to your 20, and it'll return your original t. So your t won't change, but when you come back here and you examine t, you'll see it pointing to a 40, but if you look at the left node, it should point to a 20, the left pointer. And 20 should have null pointers. And 40's right pointer should still be null. And then go through and insert 5 or 6 nodes and make a nice big tree like that. And then do one more insert and trace through it line by line in GDB and watch how it's sort of deciding which way to go and how this temp variable is changing. And if you go through all of that, by the time you can make sense of that, you're going to be in really good shape as far as how this thing is laid out in memory. All right, so this is one way to do an insert routine. It's what we would call, I don't know what I would call it. I'd call it procedural or sequential. It's based on our pencil and paper approach of move to the left, move to the right, move to the left, and so on, and then stick a new node down there. And so instead of moving our finger around, we have a temporary pointer, and we loop, keep going back up to the top, so you need some kind of while loop or something, but this is effectively a jump back up to the top as we move through. And when we get to a point where we say, okay, we want to go to the right and there's nothing there, then we do this, and we stick our new node on the right, and we exit. So that's a procedural way. There's a totally different approach we can take. And this is based on the following observation. If this is our tree and we want to insert a 56 into here, we know that everything to the right of this root node is going to be bigger than 40. And everything to the left will be smaller, right? That's a binary search tree. 56 is bigger than 40, so we know 56 is going to end up somewhere in this subtree over on the right. Well, if I have a friend who knows how to insert into a tree that's this big, I can insert into a tree that's one size bigger. I just decide which half of the tree I want to insert in. I hand that tree to my friend and I say, insert that node into there. They hand me back the tree with this new node inserted, and I just plunk that down right here, and I'm done. Everybody catch that? So I've got a friend who can insert into a short tree, and I decide I'm going to make a living by inserting into trees that are this big. Someone gives me a tree this size and says insert a number. I just figure out which subtree it's supposed to go into. I hand that tree to my friend and say insert into this tree. They give me back the tree with the node inserted, and I just replace either the right subtree or the left subtree, and I hand that to my customer. All right, so that's the nature of recursion, except that your friend who you're handing this to is actually yourself. So what would this look like? So we want to insert a node n into this tree T. We're going to return the new tree. All right, we still have this edge case. It's possible that our tree is null to begin with. And in that case, there's no subtree that we need to insert to. We just make a node, and that becomes the root. So let's code that up first. If T is null, then new equals a new node, data equals n, left and right equal null. We're obviously in pseudocode now, and I'm just going to return that new node. So that's our edge case where the tree is empty to start. We simply create a new node, set the data to n, set its children to null, and we return that, and we say, here's your tree with a single node in it. If we're not in that edge case, if our tree already has some stuff in it, we're going to do that thing that I just described, which is first we're going to figure out whether we're inserting to the right or the left of the root. So if T, arrow data, is bigger than n, then we want to insert into this left subtree. So I'm going to call my insert routine and say insert n into the left subtree of T. And that's going to return a new tree that includes this new node. And I want to replace this left subtree with that new tree. So I'm going to say T arrow left equals insert. And I'm going to return tree T. If this was not the case, then my number must lie to the right of the root, and so I'm going to do the same thing. T arrow right equals insert T arrow right, comma n, and then I'm going to return T. And that's my whole routine. This is recursion at its finest. The only time we ever create a node is when T is null, in which case we just create a single node containing our number and we return it. Otherwise, all we do is we just call insert. We call insert and we return whatever the tree is that came back from insert. But as long as we believe that insert will work correctly on the left or right subtree, this will work correctly on the original tree. And you prove it by using induction, and you show that if your tree has a height of -1, meaning that it's null, then this is the code that will fire, and this will successfully insert that node into the null tree. And if it works for height n, or height h, you can work through and see that if your tree has height h plus 1, this is also going to work. Because it only requires that insert work on a tree that's got one lower height to it. So this is a good algorithm to code up the sequential one and to look at in GDB. But we're going to move more and more towards thinking about this stuff recursively. And the short version is, how do you insert into this tree? If the number is bigger than the root, insert it into the right subtree. Otherwise, insert it into the left subtree. End of story. So we want to be able to code this. And you'll probably code both for TA4. All right, how about searching? So we want to search a tree for some number n. And again, we can start with the root. If that's equal to n, we're successful. We just say we found it. If n is bigger than this, move down to the right and repeat. If n is smaller than this, move down to the left and repeat. If moving to the left or the right brings us to null, we're done and we can say that node's not found in our tree. So temp equals t, and we could say something like while temp not null, if temp data equals n success, if temp data is bigger than n, temp equals temp left, else temp equals temp right. And we go back to the top of our loop. So again, temp is our finger. If it matches the data, we're done. Otherwise, if our number is bigger than what we're pointing at, if the data here is bigger than the number that we're trying to insert, move to the left, otherwise move to the right. So set temp down here, and that's bigger than 56, so move to the left. And if we're searching for 56, we'll see that 56 is bigger than 55, we'll move to the right. Now temp will be null, and we'll kick out of our while loop. And so down here, once we exit our while loop, we know our data is not found. So that's a sequential algorithm for searching, and it's just following through. Here's a recursive one. So if the root data happens to equal our number, we're done, we found our number. We got lucky, it was right at the root. If the number we're looking for is bigger than the root, then if it's in the tree, it's got to be in this right subtree. So let's just search T arrow right for our number, and let's just return whatever value that returns. So here we'll return 1. So if the root data matches our number, we're done. Return a 1 success. If our number is bigger than the root data, search the right subtree, and whatever that search returns, return that as our function value. So if it finds it in the right subtree, we found it in our original tree. If it doesn't, we know it's not in our original tree because it could only be on the right. Else, if n is less than t arrow data, return search t arrow left, comma n. So we only ever compare to the root of the tree. And the only time we claim success is when the tree that we're searching has a root node that's equal to the number we're looking for. But if we're looking for a 55, eventually we'll call search with this tree containing just a 55. And that'll return success, and the success will bubble all the way up through. So what am I missing from this search routine?
If it's not in the tree.
If it's not in the tree. If it's not in the tree, if I'm searching for 56, I'll search this tree, I'll search this tree. 56 is bigger than that, so I'll search this empty tree, which is null. And as soon as I say, let's look at that tree's data value, I'm going to segfault. So we need an edge case up here, which is simply if t equals null, return fail. Didn't find it. So it's kind of weird, right? The only time we actually compare any data is when we compare it to the root. And that's the only time we actually say we found it. And the only time we say we didn't find it is if our tree is empty. But everything else happens because it's recursive. So this call to search will cause another call to search, will cause another call to search, and eventually one of those calls will return. And as soon as it returns either success or fail, this will return the same value, which will come back to the previous version of this, which might be here, which will return success or fail, and everything returns right away, and we pop out of our routine. All right, back to tree traversal. So we can write something closer to real code here. If our tree is null, we don't have to do anything. There's no nodes to print out, so we just return. Otherwise, traverse the left subtree. Print out the root node's data and traverse the right subtree. That's the whole program. So if the tree is null, we can't do anything, and there's nothing to print. There's no nodes in there. If it's not null, we know that TRO left exists. It could be null, or it could be a root node of some subtree. But we know TRO left will not throw a segfault. Right? As long as T is not null, it's pointing to some node, and so the thing it points to has a left and a right child. This is the left child, this is the right child, and this is the data. So these are safe to query as long as T is not null. And this will faithfully traverse the entire left subtree and then print out the root node, and then traverse the entire right subtree. And it's a nice recursive tree traversal. And it does it in order, left node, right. We could try to write that without using recursion. And I may have you do that too for PA4, because it's a fun exercise. But how would we traverse this structure if we weren't going to use recursion? Here's a rough idea. So start off with temp pointing to the root. All right, if temp left is not null, we know we need to go down to the left and do some traversal first. So here's what we're going to do. We want to save temp on the stack, so we push it. And then we change temp equal to temp arrow left, and we come back up. And if temp left is not null, we're going to push this on the stack and move temp down to here. So our stack looks like 40, and we move temp down to here. Temp left is not null, so we're going to push temp, which is 20, and we're going to move temp to temp arrow left. And these aren't numbers I'm pushing on the stack, they're actually nodes, right? So it's the whole address of that node. So we come back to a 10. If temp arrow left is not null, we would do the same thing, but it is. So we're going to print temp arrow data. So we'll print out a 10. And then we want to pop up one level. So we'll say temp equals pop, which will pop the 20 off the stack and point here. And now we're going to, and this is just to give you an idea, we'll talk about this more later. Now we print out temp's data, which is a 20. And then we're going to set temp equal to temp arrow right. So temp points over here, and we're going to go back up here. And so if there's other stuff hanging off here, we'll go through the same procedure of parsing that up. In this case, temp left will be null, so we'll print out temp data, which is 25. We'll set temp equal to pop, so temp will come all the way back up to our 40. And we pop that off the stack. We pop the data, and then we set temp equal to what's on the right. And we come back up here. Temp left is null, so we're going to print out the data, which is a 50. I have one too many pops. I need another push somewhere. Like I say, we'll work out the details when we actually do this as a programming assignment. But the idea is we're going to use a stack to remember where we are. And each time that we finish and we come back up to the top of the loop, we'll pop off the last thing that we pushed. And then we'll continue the traversal from that point down. But I need another push in here somewhere. Otherwise my stack will underflow. So there is a way to do this sequentially, but this is a much shorter 4-line algorithm. So what's left? We can insert, we can search, we can traverse. What haven't we done? Delete. Delete.
Or just call search until you find it.
We could. That wouldn't be a bad thing to do in the beginning because you don't want to try to delete if you don't have anything to delete. Don't try to write all this.
You don't want the search to return the value of the node though, right? Or
Search is usually just returning a success or fail. All right, so how do we delete a node? Well, first we can somehow find the node. And there's a few possibilities, so find node to delete. And there's three possibilities. So case one, let me call this node n. Case one, n is a leaf. For example, we want to delete 79. Pretty easy to do. Just erase it. All right, how do we do that in code? As we're moving through our tree and we're coming down and following to the left or the right, we have to remember where we came from. Right? If we're looking for 79 and we're sitting here at the 80, we can't just throw away our pointer to 80 and change it over here. We need to remember the previous node. But we look to the left and we say, oh, here's our number that we want to delete. It's to the left. And we observe that it's a leaf node. It has no children. All we got to do is free this node from memory and set this node's left child to null. All right, so find node n to delete. Let P be the node right before n, immediately before n. So we're coming through, this is P, this is n. And we find that n's data value matches the thing we're trying to delete. If n has no children, just set P's child to be equal to null and free n. So free n, set P left or right equal to null. And we need to know not only the previous node, but we need to know to get from the previous node P to the node n, did we go to the left or the right? So we need to do some housekeeping here. We need to keep track of the node that we were at before, and we need to remember which way we went from that node to our current node. And then just use that to set either the left or right child equal to null. That's the easiest of the three cases. Case 2, n has one child. So if it's a leaf, it's got no children. This case, n has a single child. So for example, I don't have any nodes with just one child. Well, let's say we deleted 79. All right, so now we want to delete 80. So we did delete 79, we did that. Let's delete 80. So we come down through, we go to the right, we go to the right, we go to the right, we go to the left, and here's 80. So this is our node n, this is our node p for previous. And we check n, and it's not a leaf node, it has one child. So,
Couldn't we set the data of n's child to be n and then free the child?
that's one option. So we could set this value to be 85 and free the child. The other option, which is the one I'm going to write down here, is,
P left equals 85.
yeah. So, set P left or P right equal to n's child, and then free n. Some more housekeeping. So we check n, see if left and right are both null. If it is, we do this case. If one's null and the other is not, the one that is not null, that's its child. So take P and set, in this case, its left pointer equal to the child, and then just free n. And so that's going to basically do this. And then we free 80. And this is nice because we're not moving the data around memory, and the data could be, you know, a hash table with 1,000 cells in it or something. So this lets us just change what the parent is pointing to. All right, case 3 is obviously going to be the more interesting one, but it's not too bad. So we've deleted the 80. Let's delete the 25. No, let's delete the 40. Let's make it really hard on ourselves. We're going to delete the root. And we clearly can't just free this node, right? Because that's what's pointing to everything else in our tree. So we have two options. And we can do either of these. And in your code, you'll probably just pick one to do, or I'll tell you one to do. But we might alternate, or we might choose one over the other. So let me just show you option 1. So find the largest node in the left subtree. Swap that node with n, and then free n. So we want to delete the 40. Let's go into the left subtree. That's this thing right here. What's the largest node? 27. So all we got to do is replace the root with 27, get rid of this. And we're done. Now, if we're actually doing this, without just copying the data, here's what's actually going to happen. I'm going to free this node. I'm going to change 27 so its left pointer points here, and its right pointer points here. And I'm going to set 25's right child to be null. Okay, that's what it would actually look like in memory. So swap this with n is a whole lot of operations, right? So set so find the largest node in the left subtree. Let's call this node L. So how do we swap that with n? So I'm going to say set L's parents right or left child equal to null. So that breaks this connection to L's parent. then set L left equal to N left, and set L right equal to N right, and then free N.
But does that only work? Should work.
Should work.
Because it wouldn't be children.
Yeah. So this will work because if we're in the left subtree and we find the largest node, it's got to be a node that has no children. No, that may not be true.
Yeah.
It could have a left child. But we know how to delete if you only have one child. So let me be careful how we do this.
Then perform as the last,
Yeah.
second step, you want to perform that prior to delete function.
Right, so you're going to set L left equal to N left, L right equal to N right. I'm going to free N, and then I'm going to delete N, L. And L cannot have two children, because if it has a right child, that right child is bigger than the root. So this is either a leaf node or it has a left child. And in both of those cases, we know how to delete. Right, that's possibility 1 and 2. Possibility 3, we change this node to point to the things the root used to point to. We get rid of the root, and then we use one of those cases, 1 or 2, to delete this node from the tree. And if it's a leaf, we'll just get rid of it and change this to null. If it has a left child, we'll simply change this to point to the left child. So the effect of this is 27 becomes the root. And everything else is fine. So now let's delete the 27. And let's do this in pieces. So we've got 27, 20, 10, 25, 22, and then other stuff over here.
N was a temporary, right?
Yeah, everything's temporary except the original root. All right, so we want to delete 27. So 27 has 2 children, so we're in case 3. And we're just going to stick with this, find the largest node in the left subtree. So here's the node N we're trying to delete. The largest node in the left subtree is going to be 25. All right, so we're going to basically swap that with our root node. So our root node is going to become 25, which we do by basically, eventually this is going to point over here, and the right child of 25 will point here. So this will put the 25 up here. And we're going to free the 27 node, and then we're going to call our delete routine, actually before we move the 25, and say delete 25 from our tree. So you need to be careful of the order here. How do we delete 25 from this tree? It's smaller than 27, it's bigger than 20. We come down here, this is the node we want to delete. It has exactly 1 child. So that puts us in case 2, and has 1 child. So set either its parents left or right to that node's child, and then free the node. So how do we delete the 25? it came from this node, 20 to the right, so replace 20's right child with 25's only child, 22. So this becomes a 22. And then we go ahead and replace the root with our 25. And there's our new binary search tree with the 27 deleted. So it's a combination of behaviors, right? It's starting at the top, it's marching through, it's keeping some memory of where we were and how we got to where we are, whether we went left or right, and then breaking it into 3 possibilities. If it's a leaf, if it has 1 child, and if it has 2 children, we have to do some adjustments, and then we recursively call the delete function. And we know that this time when we call delete, the node we're deleting will either be a leaf or have only 1 child. And so we do one of these.
So for that second option under cast 3, couldn't we have just set the data value of n to equal L, and then we just perform the second cast on L?
Yeah, so we can just change the value instead of doing this. But again, if it's a lot of data, we may not want to do that, or we may have to copy all the pieces individually.
Well, considering we're going for the rightmost node on the left side, we would just have to search for it once we find it. All we'd have to do is just swap the data values and then delete that one node, move the child up.
Well, yeah, so swap it, and if there's no children, just delete it. If there's 1 child, basically swap it and free it. But what we're going to find sometimes is that we're storing a left pointer, a right pointer, and an integer data, but we may have some other stuff in here. We may have a struct, payload, more. And that could be some big, huge, deeply nested structure. And if we want to copy, we need to actually go through and do what's called a deep copy. Copy all those pieces. So it's easier and probably faster if you just change the pointers. But, well, it's faster, but it's more complicated code-wise. All right, so when we actually get to PA4, which won't be until next week, we'll go through this more carefully. But these are the basic operations on a binary search tree. So initialize it, insert, search, traverse, delete. Okay, delete being the hairiest, but if you go through it step by step, it's really not bad. And if you have a good insert routine, you have a good traverse routine, you can use those to debug your other routines, right? If you want to delete, make your first modification and traverse the tree, see how it looks, take your next step, see how it looks, and so on. But it's one of these things that can be very long to debug, because one wrong pointer and everything is totally different. All right, so we'll talk about PA4 on Monday, and we'll look at these routines in that light.
And we'll talk about Monday, sir.
Say, oh, Monday's a holiday. All right. I'm going to have to push PA4 back then, I think. I might push PA4 back. I'll look at it. I'll post it up anyway, and you can take a look at it, and parts of it you can definitely get started on. The init and the insert should be fine. Search should be fine. Traverse should be fine. We should be okay. But we'll have to talk about delete on Wednesday in more detail and go through that. And then after that, we want to talk about balancing trees. How do you insert nodes so that if you insert 10, 20, 30, 40, 50, 60, 70, you don't end up with a lopsided tree? And it's a pretty straightforward business. So here's 10, here's 20. If you're going to insert a 30, that's lopsided. Do what's called a rotation. Bring this up to the root, bring this down to the left. So now you have 10, 20, 30, and it's balanced. And we add another 40, and that's still technically balanced. We add another 50, and that's going to be imbalanced, but we can rotate this, and it'll be a 20, 10, 40, 30, 50, and that'll be balanced. And we always need to do one, possibly two of these rotations, where we take something like this and turn it into this. And if there's other stuff hanging off of here, it just continues to hang off of there. I may or may not have you code that. There's too many things to code in this course. And we've only got one more after PA4, so I may have you do some paper homework or something for this, because it's cool algorithms. All right, that's all I got.